So yeah, it's a great pleasure to have Ioannis with us today, and it's great that we have him here for the whole month, even though the Academy of Athens kept him for a few days.
Well, okay.
He's going to talk to us today about mathematics for data-driven modeling, the science of crystal balls.
Mickey Mouse. Thank you. So first, it's a great pleasure to be here again, and to see so many friends, and it's an honor to be invited to be the Rothschild Lecturer. I am grateful to the organizers for the many things that they did to make this so interesting scientifically and otherwise. However, I am a little concerned because all the Rothschild funds are going to be paid after we leave, and I worry about the value of the sterling after Thursday, but I very much hope that Britain stays. Not for this reason, for more historical and cultural and other reasons.
But Ioannis, we bought the beer first.
The beer, certainly, yes, that is true. So this is an extremely pretentious title. We were thinking with Rafi Koifman about writing a DARPA proposal with this title, and we thought that even they would laugh. But I thought, what the hell? This is, it's the end of the day, and there's beer afterwards, and so I will kind of try and make some sense of what I mean by saying this. This is kind of a more reasonable title for those of you that know me. No equations, no variables, no parameters. This is a talk I gave. It's a version of a talk that I gave in Berlin around a month ago. They had the birthday of the Zuse computer, which was a Z1, which was the first programmable computer, which was even before Enigma, and was done around 1941. And I'll tell you a few things about this Zuse guy, who must have been pretty smart and was not a Nazi. He did fight in the war like a normal soldier, and the computer was built in the living room of his parents. There is like some photographs, if you look in the books, about the living room of his parents. They were very tolerant parents. All the living room is full of the computer. You might expect, the work is done by many other people. Bill Gear is the Gear of Gear's method. Rafi Koifman lives close to God at Yale. Gerhard Hummer is a Max Planck director, and then the people that did the work, Ronen Talmon, in this case, who used to be Rafi's postdoc and is an assistant professor now in EE at the Technion. Elio Chiavazzo was a Fulbright scholar. He is now a professor in Torino. Roberto Covino is still a postdoc with Gerhard, and Anastasia Georgiou is one of these amazing undergrads that we get sometimes in Princeton, and I'll show you what it is that she did. And as kind of Costa said, I'm slightly delocalized this year. I'm a little bit in Berlin and a little bit in Munich and a little bit here. So the people in Berlin, they put something in the newspaper about all the people speaking in this, and they said a lot of wrong things about me because I am not a mathematician, as those of you who know me know. Maybe I'm an applied mathematician, and I really am a modeler, an engineer, reasonably proud to be a chemical engineer. And I also do not revolutionize data science. I work for a guy that does. This is Rafi Koifman, and that's the data. And then if this is too modest, I work with a guy who revolutionizes data science. And I'll explain again what it is that I mean. And actually, I guess I want... what did I do with it? Bear with me. There was one other slide that I wanted to tell you about when I actually was young and promising, which is here. This is a paper that showed up in 1986 when I was a postdoc in Los Alamos, when Soviets existed. There it is. This is a paper that first showed up was first discussed in the New York Times before it appeared in Physical Review Letters. It's a paper by Frisch, Haslacher, and Pomot. And what they did is, I think, what we have been hearing in the last few days. They were even more irreverent than we are. We said, let's do particle calculations when we don't have PDEs. These guys were worse. They said, let's do particle calculations even when we do have PDEs. They were the ones that figured out what are the right symmetry rules for a lattice gas so that you can do lattice calculations with particles. You understand, the particle is either a 0 or a 1. So calculations with particles that are or are not there on a lattice are then binary calculations, and the dream was that one would make special hardware that operates on binary numbers that are particles, and then the statistics of the particles would be the Navier-Stokes, for example, and the hell with the singularities of the Navier-Stokes, the hell with as Philip Rosenau. I don't know how many of you know him. The hell with existence and uniqueness and so on and so forth. We're going to do computational statistical mechanics to solve even the PDEs that we do have. This did not materialize for many reasons that make sense, but it was a glorious time. And the reason that I'm showing this to you is because, again, I'm a nonlinear dynamics person. I like bifurcation algorithms. That's what I really like. And I remember hating it at the time that all the algorithms, you know, they were my friends that were postdocs with the guys that were doing lattice gases, and they were doing Rayleigh-Benard, and I was doing Rayleigh-Benard with the Navier-Stokes, and they made movies, and I made movies, and our movies looked the same. But all the tools that I knew and loved, the steady state calculations, the stability calculations, the parametric sensitivity, you know, branch following calculations, all of this stuff was completely useless. This stupid thing doesn't even have a steady state. It's just running around stochastically. And the only thing that you can do is that you can make movies and then show them to your friends. And so, some of you must feel this, right? We make these simulations, but all the beautiful things that we can do with you know, we can do direct simulation. Well, okay, we can bias the simulation a little bit, but all of these beautiful things that we can do with continuum stuff, we cannot do with the calculations that we are doing now. And so it's not as if for a long time I really was working on how to deal with this, but what I'm going to tell you today is a summary of many different pieces of 15 years worth of work that have to do with how do you still manage to do bifurcation calculations even if you don't have equations and variables and parameters at the macroscopic level. So this is Julio Tino, who is a dean at Northwestern. He's also an artist. He's a smart guy. He made this thing. I stole it with permission. He says there is simple systems, a few degrees of freedom, complicated systems, many degrees of freedom, but every degree of freedom does a special job. And then complex systems, many molecules, many reacting particles, many fishes, many people, and then order emerges from the interactions. His point was to contrast complicated and complex. My point is to say that this is simply, if you think of it as billiard balls, each of which is a sphere that has a center, has a mass, and has a momentum. If you think of it as atoms, then it is horribly complex. And if you try to enjoy billiards computing the wave functions of every electron in all of these atoms, it would not be fun on Saturday night. And the point then is that simplicity is at the level at which we can usefully model something, because really everything is complex. And this is my kind of demo, one of my favorite demos of a complex system. Comes from the work of Tony Roberts. Here is a whole bunch of particles. These are two views of the same thing. This is a bunch of particles. They start being 20,000, but later on they change. They're supposed to be microorganisms on the surface of the sea. They multiply, so there's birth and death. There is random walks, and then there is stirring by an advective messy field whose details I'm not giving you. And my point in showing this is that I'm going to show you two movies of the same thing. These are the particles. These are the statistics that matter, which happens to be, trust Tony Roberts, the pair correlation function. If you run this movie, then you're going to see that while on the right you have a very nice evolution of something to a steady state, maybe with a little bit of noise. On the left, things are, we can't even tell, is it stationary? It's a mess. They're running around. There's striations that are formed. There's all kinds of stuff. And the basic idea, again, is that the same thing has very, very different properties depending on whether you're doing the direct simulation or whether you're doing the coarse-grained PDE, if you want, evolution. And so this was the first thing that we did. This was with Bill Gear 100 years ago, in 2001, I think. This is the first of these algorithms that we did that we call equation-free. This is coarse projective integration. What's the idea? The idea is somebody has told me that there exists an equation for the pair correlation function, but I'm not smart enough to know what it is. I'm not smart enough, or I don't know enough math to derive it from the particles, and Landau is dead, and I cannot ask him what the equation is. So I do, however, have the fine scale code, the particle code, and I'm thinking if I had this equation and I was going to integrate it, if I did forward Euler, I would need a time derivative. So given an initial condition in the pair correlation, given an initial pair correlation function, I'd like a time derivative of how the pair correlation function would change. I don't have an equation, so I don't have a right-hand side, so I don't have a time derivative, But I take an initial condition, bless you, I make it particles, I run the particles a little bit, and I observe them. So I do an experiment with my code, with my particle code. I observe the evolution, I estimate the time derivative on the fly, and make an Euler step. Then I make particles that have this pair correlation function, run for a short time, estimate the time derivative, make a step. This is the basic idea in all of this equation-free stuff. If you had the equation, what would you need? Would you need the right-hand side? Would you need the Jacobian? Would you need the residual? Do just enough experiments, appropriately initialized experiments, appropriately observed experiments, appropriately, estimated experiments. You need to look at this movie. Maybe you need several copies of this movie in order to estimate the time derivative. But basically, anything you would get from a formula, you get it from a brief experiment with a particle-based code. Here it's just integration. What do you save? You save that you don't have to integrate all of this time. You integrate just a little bit. How much a little bit? Oh, it depends on the separation of time scales between the fast modes and the slow mode. So the idea is that there is a separation of time scales that goes hand in hand with having a macroscopic equation, and you're taking advantage of the conceptual existence of this to save time. The important thing, well, what are the rules of the game? I'll tell you what the rules of the game are, but the most important thing that I want to kind of stress here is that in order to do this, you must know what the right macro quantity is. And in this case, Tony Roberts told me in his paper that the right macro quantity is the pair correlation function and nothing else. I'll get back to this. That's a lot of my talk today. So this is just to show you that this works. Pair correlation function is a function of the radius and time. Blue is running all the time the particles. Red is run the particles for a little bit, jump, make particles with this pair correlation function, run a little bit, estimate the time derivative, jump. What do you save? Not very much, but it's a conceptual idea. The basic idea is you use smoothness. So you see this fits. We are in Cambridge. This is the Newton Institute. This is calculus. In the right variables, you take differential. Well, okay, not differential, but you take the first term in the Taylor series. You use derivatives, so you use calculus, but what is the difference? The calculus is in the right variables, and the right variables is not the positions of the particles. The positions of the particles are stochastic, or even if they were not stochastic, the Taylor series would be valid only for a small time. Here, if you look at the right variables that magically Tony Roberts told you what they are, these variables you can take much bigger Taylor series steps. So we are using separation of time scale and smoothness to estimate time derivatives and make big jumps. And you can do numerical analysis for this stuff. And again, if this is space, this is time, and this is the solution, you're using smoothness in the variable and in time to be able to make jumps. You also can do smoothness in space, but I don't want to talk about it today. So you don't need to run for all times and all spaces. You only need to run for little patches in space-time and take advantage of smoothness. Okay, so the tools of the trade, you need to be able to go back and forth very easily between the macro description and the micro description. You need to take particles and calculate pair correlations. You need to take pair correlations and calculate particles that have these pair correlations. The first is easy, the second is not easy. Sal Torquato, my colleague, has made half a career by basically writing algorithms for creating particles that have a given pair correlation function or other such features. The main idea is, don't put effort into getting a good macro equation. Put all of your effort in getting a good micro model, and then all of the benefits come from the way you process the results of the short bursts. So this is effective simplicity. Use derivatives, use smoothness in the right variables. Use smoothness in time of the macro stuff to jump the macro stuff. Use smoothness in parameter space of the macro stuff to do parametric sensitivities. Use Frechet derivatives, estimated Frechet derivatives of the macro stuff to do Newton. Use derivatives in physical space to not do the calculations in all the physical space. Just do Taylor series, but do the Taylor series in the right variables. And so this is the main thing now, right? This is well, it's one of the main things. I wonder, how do you know what the right macro variables are? I mean, yes, we know it is concentration and temperature for basic chemical kinetics, but as you all know, who knows what the right reaction coordinate is for something? Who knows how many moments of a distribution we need in order to write something that is deterministic? So where do variables come from? Sometimes they come from a systematic hierarchy. You know, you keep enough moments of a distribution, hell, you're going to describe it. Sometimes they come from letting your brain figure out the right thing. You look at the problem for a couple of 100 years, and you kind of know that for fluid mechanics, maybe density and momentum are good variables to describe what happens. Or you ask somebody who is very smart, or you have a very good mathematician friend at Courant, let's say, and you can do the 13 moment closures, or you can do, somebody who is smart tells you what the right variables are. And then the other thing is what I'm going to talk about today, is to kind of try and go surreptitiously to the computer science department and see what these guys are doing in terms of machine learning, and use the machine learning tools to find the right variables for us to do our modeling. So somehow the idea is, let's not be computer scientists, take the data and do the data mining. Let's try and be a little numerical analysts and a little bit computer scientists. Produce some data, do a little bit of data mining in these data, and then use that to help collect the next data, do a little of data mining on those data, use that to go and collect the next data. Let's try and get the machine learning to be part of our usual numerical algorithms. Okay, so data mining. 150 years, principal component, singular value decomposition. I have some data points that need a lot of variables, 3, and then they can be reduced by the principal components in much fewer variables, 2, so that instead of describing every point with 3 numbers, we need only 2 numbers. What is the point? The point is, if we have a code that has 3 equations that produce these data, if we know that the data are 2-dimensional, then we can write 2 equations that produce these data. So the idea is that if we find coordinates that parameterize the data through data mining, those coordinates would be good variables in order to write models with. And all of those that have done proper orthogonal decomposition in fluid mechanics know this. You get empirical basis functions, and then you do Galerkin with the empirical basis functions, right? So do data mining to tell you what the right variables are. You're going to tell me, if you do chemistry and principal components tell you that the right variable is 0.7 carbon plus 0.2 hydrogen plus minus 0.9 oxygen, that's not a very good chemistry variable to do chemistry with. I don't care. I can write evolution equations for this thing, so I can do beautifully predictive stuff with variables that are horrible in terms of human understanding. Do I make my point? You have some set of coordinates. You can write evolutions in these coordinates. You can use them to do beautiful predictions. That doesn't mean that the variables that you're working with are as beautiful and as easily understandable as concentration or temperature. Even in principal components, even with linear data mining, the variables that you get are not physically meaningful. But you can work with them. So we don't do principal components. We do nonlinear principal components or kernel principal components. Or, you see, I work with Rafi Koifman, so you would expect I do diffusion maps. You're very welcome to have your own Poisson. You can do isomap. You can do other kernel principal components. You can do local linear embedding. You can have your own set of tools. The basic, all of them, if you're careful, will work. Maybe some will be a little bit better than something else under some circumstances. That is not the point. I get a lot of simulation data, and then every node is a simulation point from some big code, and then I create a graph out of these data. I guess Belkin and Yogi create a graph out of these data, and then Rafi and Stéphane Lafont, his student, create a graph out of these data, and now many, many people create graph out of these data. They connect these data points by an edge that has a strength, and this strength comes from a kernel. So this is the kernel part. And the kernel has in it a metric that I know and understand. It is the kernel in the original space in which the data were obtained. There is a metric there. And then there is a scalar. And what does this scalar do? If this distance is much bigger than this value, then the points are effectively disconnected. So you believe distances if they're small. You don't believe distances if they're big. You create a Markov chain out of the Markov matrix out of this process. You do eigenanalysis of this Markov matrix. It almost looks like doing principal components, but because of it being done this way, you look at the eigenvalues that you get and the eigenvectors that you get, and the basic idea is these eigenvectors are good variables for describing the data. There is no nice words for describing them, but they're good variables for describing the data. And therefore, they're good variables for writing models of the problem. I asked Carmelin Silva, my grad student who finished and went to the dark side, she works for Bloomberg now, and to make some sort of educational slide for this. So this is my educational slide. For those of you that don't know diffusion maps, bear with me, don't worry about it. For those of you that don't, maybe this is, let me say, this is something that I wish somebody had told me when I started. It would have saved me probably a couple of years. Well, even though it's ridiculous, it took me that much to understand something so simple. So take this parallelogram. You do the eigenfunctions of the Laplacian in this parallelogram with no flux boundary conditions. You remember you're like, I don't know, it's even undergraduate, boys and D', you're going to get cosine x. The interesting thing, well, first you're going to get a constant eigenfunction, which is the equilibrium for diffusion in such a domain, and then you're going to get cosine x. And this is the points colored by cosine x. And the big thing, the amazing, the major insight, you know, that you get in this is that if you have points between 0 and pi, between 0 and pi, cosine x starts at 1 and finishes at -1, and so cosine x is 1-to-1 with x. And so if you order your points by the first eigenfunction of the diffusion, it's the same as if you ordered them by x. So you can think that diffusion discovered the x coordinate. And if you find a few more eigenfunctions, the first few are going to be harmonics of cosine x, but then at some point after a few eigenfunctions, you're going to find cosine y. And cosine y gives you an order in this direction, which is the same as y. So you can say, the first and seventh eigenfunction of diffusion found the x and y coordinates. That is, they gave you a set of coordinates on this parallelogram. And now forget the parallelogram. Take a bunch of data on the parallelogram and do exactly the same thing. This is like a discretization of the domain. And if you do Laplace, the graph Laplacian on the graph based on this data, you're doing a discretization of the eigenfunctions of the Laplacian. And here is a pretty good approximation, discretization approximation of the cosine. And you see that if you color these points, by the first eigenfunction, you are basically finding the length of this ribbon. And if you wait a little bit, you're going to find the width of this ribbon. And if you take this two-dimensional ribbon and embed it in 10-dimensional space and curl it around and whatever, you do exactly the same graph Laplacian. And in effect, you're doing exactly the same calculation. You're doing Laplace-Beltrami on this manifold, and the eigenfunctions of Laplace-Beltrami on this manifold are going to give you the length of the ribbon and the width of the ribbon. And so doing graph Laplacians, or in general doing manifold learning, or in general doing harmonic analysis on data, or in general finding the eigenfunctions of the appropriate matrix is going to give you beautiful coordinates describing the data, and these are good variables to write models with. They are empirical basis functions if you want. So I asked Carmelin to do a fun other domain, and she chose this kind of Starship Enterprise kind of thing. And here are the points, and then the first eigenfunction will give you the azimuthal direction, and then the seventh eigenfunction will give you the radial direction, and the ones in between will be harmonics. And so you can see for this weird domain that if you sample it enough and you do things properly, you are going to get coordinates on the data. And coordinates on the data are good variables to work with. And so if they're good variables to work with, we can write models with them. And let me kind of go back to this. So this, if you Google isomap, you get this Swiss roll. It's very important to say, why is this useful? It's useful because if you had these three-dimensional data and you did principal components, there is no line that passes through this data. There is no plane that passes through this data. You need 3 dimensions in principal components to pass through this data, and 3 dimensions are one too many. You do linear data mining, you're going to get way more variables than you could. And if you do diffusion maps or a lot of other things, then you're going to discover, if you want to unfold your manifold. So is this useful? So this is my some actual research. This is something that starts a long time ago. So let's say that you want to fold a protein computationally, and here is the well, and most of the simulations are sitting at the bottom of the well. And if I try and go forward in time, well, I will keep staying at the bottom of the well until some rare event happens. But if I have a good reaction coordinate, I can use these simulations to have a parametrization of the support of the effective free energy. And what I can do is that I can go to the edges of the part of the support of my slow manifold that I have explored, and then try and make a Taylor series, not of the dynamics, but of the geometry of the problem. What do I mean? This is something from a long time ago. This is with Gerhard Hummer and with Bill Gear. I was so happy when I first thought of this. The paper was called Computing in the Past with Forward Integration. What is it that you do? You run, remember the issue, you run a little bit forward in time and then you come down on a slow manifold and then you estimate the time derivative. And then remember before you do a jump forward in time. Well, why not do the jump backward in time? You do a jump backward in time. So this is forward Euler in reverse time. You go backward in time. Okay, of course you get off manifold, but then you start here and run the detailed problem again a little bit for a short time. Linear errors backward, exponential corrections forward. You can do a big step and then just a little bit, a big step and that just a little bit, and then you can effectively go backward in time. So for those of you that were here in the morning and heard the other Kostas' talk, there is an element of kind of going effectively backward in time, going up an effective free energy well. And that's what we did with Gerhardt back then. This is cute, but it is a little bit cheating. Let me tell you what is cute and what is cheating. So this, let's say, is an effectively one-dimensional well for alanine dipeptide in terms of one of the usual dihedral angles. You start somewhere, you run a little bit forward, you estimate the time derivative of the average of several runs. That gives you the local gradient. And then you go a step up. You run forward molecular dynamics a little bit, estimate the local gradient, you do a step up. And so it takes 4 steps to get out of the well. 4 brief bursts of forward molecular dynamics to get out of the well. Of course it's one-dimensional, but the big cheating is not that. The big cheating is I know what the right reaction coordinate is. If I know what the right reaction coordinate is, then it is ridiculously easy. I just do umbrella sampling on a grid of 100 points or 10 points or 20 points and I know everything, right? The thing is, even if it's one-dimensional, the one-dimensional is not the problem. The problem is, what if it is one-dimensional, but I have no idea where this one dimension is in conformation space? Well, here's what you do. You do a little bit of molecular dynamics, and you kind of figure out that it's effectively one-dimensional, and then you go to the edges of what you have fathomed, and then you do a Taylor series in the reaction coordinate. You do a Taylor series in the reaction coordinate that is going to take your conformations a little bit off the slow manifold. It's okay, you can start here and use something like plumed, which we did in this case, or even you do unbiased simulations if you are not too far off, and then you can come down back on a slow manifold, do some simulations, estimate the local geometry again. And now that you have the geometry, you, as I told you, you can go this way in the geometry, which is down in effective free energy, and the molecular dynamics would go there by themselves very happily, or you can take the geometry upwards in the direction that the molecular dynamics would not like to go at all. So the idea is that you can do Taylor series in the geometry of the low-dimensional problem. You see, it has to be a low-dimensional problem. You just use your molecular dynamics to sample a little locally, and having sampled a little locally, you can extend the geometry. And it is extending the geometry that is what you use to bias the next collection of molecular dynamics. So here is the same thing in 2 dimensions. So this is my effective free energy surface that is some sort of magical carpet in high dimensions. I don't know exactly how it is, but let's say it's 2D. So I do a little bit of molecular simulations, or Monte Carlo. I mean, we can discuss this. Or you can even do umbrella sampling somewhere. But just, let's say, a few unbiased simulations. By the way, the effective free energy is some sort of color pattern on this carpet. I may want to take it into account. I may not want to take it into account. I will explain. So you run for a little bit. You get a lot of data. You do data mining. You figure out they're 2-dimensional. You find the edge of how much you have fathomed. And then at the edge, if it's 2-dimensional, what you do is that you basically use Taylor series. In what variables? In the adaptively determined parametrization of this little 2-dimensional cloud. You can do little local principal components. You can do, for those of you that know, you can do geometric harmonics based on the diffusion map parametrization. But it's just Taylor series. You do Taylor series, and then you make a prediction of where the thing is going to be in the geometry. You initialize there, you get some low-dimensional stuff again, you get the boundary of that, you're going to get local principal components. You can kind of see how you can parallelize this. You can start all around the 2-dimensional boundary if it's 2-dimensional, all around the 3-dimensional boundary if it is 3-dimensional. As long as it is low-dimensional, you can basically fathom the carpet. And the other thing that's important, which way do you go? Well, you may not take into account the effective free energy at all. You can just take into account the geometry. Start at the edge and do geodesics going outwards. We did that. We have another paper with Gerhard Humer, but again, we were cheating because, and Thomas Fruin, it was nice work, but it was cheating in the sense that we knew what the reaction coordinates were. Here, we are building the reaction coordinates as we go. So if you do a little short local run, you can use the run, there was several discussions about this, to estimate the local drift and diffusivity. And if you have the local drift and diffusivity, that is, if you allow yourself to see the color pattern on the carpet, if you want, you can move in ways that have to do with this carpet. You can go upwards in effective free energy. You can go along level curves. You can go in whatever way you want. But the main point is not this. The main point is you do geometry. You do not try to accelerate the calculation. You're trying to sample the effective free energy surface. Clearly, there is something nice to trying to go effectively backward in time from the bottom of a well, which again has a little bit to do, I think, at least I feel that spiritually it has a little bit to do with what Kostas Pilotopoulos was saying this morning. Okay, so you get some data from an unbiased little run, and then you use something to find where the boundary of the data are. We've written our own codes. Turns out alpha shapes that you can find in MATLAB is as good as anything. So you find the boundary. Here is a regular one. Here is one that comes from a simulation. And now that you have figured out what is the dimensionality of the data and where the boundary is, you just do Taylor series. Okay, you need a little bit of differential geometry, but you can do local planes and local PCA. As I told you here, you can do the normal diffusion maps and do geometric harmonics. There is something else that's sign diffusion maps. If you know the boundary, you can do it a little bit more interestingly. It is not so important. Think local principal components. The important thing is cloud, boundary, local principal components, and then jumping, biasing. It is the biasing that is important. The biasing is important because, well, if things are flat, you don't need to bias very much. They will go away by themselves. But if you bias, you can save some time. The big thing is what happens if there is a potential and you're at the bottom. Then the things would not like to go further out by themselves. And by doing this, by biasing the geometry, you can save, you can almost imagine. I mean, take a steep enough well and you can save aeons, years, millennia, and so on and so forth. If the effective energy is flat, you're not going to save that much. You're going to save much less. But the important thing is that if you have wells, you can get out much faster. So here is an example. This is a two-dimensional problem that has two wells, one here and one there. Things are very steep in the very stiff in the third dimension. You can see a simulation. This is a Gillespie calculation. So this comes back down very fast and then goes to the bottom of a well. And then Anastasia Georgiou, this amazing kid that I told you about, what she did is that she ran for some time. She did diffusion maps on these data, figured out they're two-dimensional, got the boundary, extended, initialized. No, I don't want to kind of do anything like that right now. Okay, so then she extended. She got some new data, amalgamated the old data with the new data, found the new boundary, jumped further out, and now just look on the left side, further, and it took her 14 iterations to get out of the well. Okay, so this is like a three-dimensional Gillespie thing. So here's a little bit of molecular dynamics. So this is alanine dipeptide. I know this is also kind of, it's not a real problem, right? But it's okay. So here is a two-dimensional problem. This is the top of the well. This is an angle, so it's periodic. And then here is a simulation where the thing is extended and it's projected on the usual two variables. Well, what you do is that you do data mining and you say it's not just a 2D projection. The data are effectively two-dimensional. This is a simulation with explicit water. It's tip 3Ps. And then you find the boundary and then you use the geometry to extend. And then after you extend in diffusion map space, you lift. You create coordinates that have these diffusion map coordinates. Obviously, you cannot extrapolate forever, and you may need to do a little bit of umbrella sampling so that you find an equilibrium. It's like coming back to a manifold. There is a prediction step, going back out, and then a slight correction step before you let it go free on the manifold again. So you get these green things, you run from them for a short time, you get a bigger set of data, you put them together with the first ones, you get a new part of the carpet, you find a new boundary in red, you extrapolate the geometry to find the new boundary in green, you lift again, you run from these guys, and basically you've folded the thing in 2 steps. The important thing is not this. The important thing is that this geometry was not known at the beginning. This geometry was found on the fly. The data were only here. These things were collected by using the geometry to bias the simulation, adding the data, making a new construction for the geometry and going further and further. And so here's a real problem. So this is still unpublished, okay? And it's really not my work. This is the work of Gerhard and Roberto Covino, and it has to do with MgA2, which is a huge thing, but it has a couple of like 30 amino acid helices that live in the membrane of the endoplasmic reticulum of yeast. Radek said about beer, so this is very important. And the theory that Gerhard has with his collaborators is that the conformation of the dimers of these helices is what makes the signal for whether this is the place where lipids are being fabricated. So this is the signal about whether you have a lot of saturated or a lot of unsaturated lipids. And somehow the signal gets out of the membrane, and I really don't know how, and they have experiments and so on and so forth. But my job is to kind of work with them to accelerate the simulation. So what is this? What do we do? This is somehow the only way getting out of this. Oh God, I didn't want to do that. Ah, yes, I did. This is the only way I think that I can kind of find where it is. Yeah, here. Well, it's nothing you have not seen in life. So this is, oh, now it doesn't want to do it. Well, anyway, this is a Martini calculation of the thing. And you heard Frank in the morning. I mean, this is 4 milliseconds, okay? 4 milliseconds, like we need to upgrade media objects. No, don't upgrade media objects. Just give me this. So you run a Martini calculation. They run a Martini calculation for 4 milliseconds, and they calculate the world for this dimer. This is the world for this dimer. It has a bunch of different wells, and these different wells are different conformations. And so, well, so okay, let's see. Suppose we don't want. Oh, now it wants to run by itself. Okay, so it runs by itself, and you've seen Martinis before, 4 big atoms into one ball. So let's say that we don't want to do all of this. So we run. We zoom in on one of these wells, and then we kind of take a conformation at the bottom of this well. These tryptophans are supposed to give you a feeling of what the conformation really looks like, because the other things are just straight to first approximation. And then what you do is that you run a few simulations at the bottom. And now that you've run a short time at the bottom, what you do is that you do data mining. You figure out this is an effectively 3-dimensional thing. And then you use what I told you before to extend this egg into being a bigger 3-dimensional egg. That gives you the yellow points. And then you start on the yellow points, and some of the short runs from the yellow points fall back into the bottom, and some of the runs go to a promontory, like here in England, Land's End. So they are in the same well, but in a place where the free energy kind of goes up, so there's no exit from there, and some of them will exit. And so the idea is that a couple of steps of this is just supposed to give you a feeling. You know, you say the tryptophans are different. This is a different conformation. So we are in a different well, and there is, I don't remember, 4 or 5 wells. But the basic idea is that 4 iterations of this do it. So I gave this talk in a place where I wanted to kind of be funny. So let's see. Oh, do I have sound? Can you help me with sound? 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 It's not the same without sound. Okay, so let's see. I'll play it from the beginning. So he is sitting in this well, and he has to go to the other well, which is on the other side. If he does not do it very quickly, his father is going to die. Can you give me the sound? There is sound. Okay, so let me stop it. Sorry for this. I should have. It's my fault? Oh, it's up there. Sorry. Yeah, it's my fault. Okay, let's hope that this is not too horrible. All right. Oh, it's again from the beginning. Okay, so this is one well, all right? And then on the other side, over here, there's the other well. And there is too many ways to go from one well to the other. And his father will die if it doesn't fold very quickly. He has to hurry. And so the thing is, he doesn't know in which coordinates to walk, right? There is this very strange space in between him and the other well. And so he has to have faith that low-dimensional coordinates exist. He must have faith. And so he puts his hand on his heart. And those of you that have seen it remember what happens. He kind of, he says, you know, maybe the phi and psi angles are a good choice. So what he does is that he goes out on the phi and psi angles. And he's lucky, because there is a path. They are really slow variables. And so, you know, he cannot believe it. Now, you guys can now see that there is a path in these angles, but he doesn't know. He just hopes that he can extrapolate linearly. And he walks a little bit, and after some time he has like faith that he can walk through. And then he, you know, he doesn't need the book anymore. He goes to the other side. And here's why I am showing you this. Because when he goes to the end, he takes a little sand and he throws the sand on the bridge. And that is exactly what we do. What we do is that we throw just in, you see, where I was giving this talk, Michele Parinello was also in the audience, and I had to find a joke that had sand in it. So, you know, in Parinello, you kind of walk and you have to pour enough sand so that you can cover the entire well. Here, you have to throw away just a little sand, just a little bit around where you are. You get an idea of the geometry, then you can make a step. And then you can throw a little bit sand around here and get a sense of the geometry, and then you can take a step. So this is the thing I wanted to show you. Now, the second thing I wanted to show you, which had more to do with crystal balls, is the following. Come on. Yeah? Okay. 10, 9, 8, 7, 6, 5, 4. Okay, so remember I told you at the beginning I'm a nonlinear dynamics person. So this is, my example is a nonlinear dynamics building block. This is Takens-Bogdanov. It is a nonlinear dynamical system that has two parameters, beta 1, beta 2, and two variables, x and y. It's nonlinear, and it is important because it is the representative of all dynamical systems on Earth on which two things go wrong. So at beta 1, beta 2 equals 0, 0, you have two eigenvalues at 0 at the same time. And I was trying to think what might be a good joke. One is you're driving, and what happens is that you lose a tire the same time that your engine explodes. And the other option is you get married to the wrong person and your mother-in-law hates you. And so you sit there, and then you know that as you make perturbations, there is it has effectively a two-parameter space, and all the possible phase portraits are around. There is four kinds of behavior. There is four codimension 1 curves. There is a topological way by which things are embedded. And what's the big thing? The big thing is that all systems in the world in which two things go wrong at the same time can be are homomorphic to this, can be brought into this normal form. This is just an example. In general, think of this as a nonlinear dynamical system that has some states, some parameters, some dynamical evolution equations, and some measurement function. And you don't know any of this. You just know that there are some inputs, and you set these inputs, and when you set these inputs, you do experiments, and you measure some outputs. And the question is, can you make a model by going directly from the data to the outputs? And this was done in 1981. You can see it's 1981 because the guy has long hair. He wrote this paper. It has thousands and thousands of citations, and as far as I can tell, he did nothing amazing after this. But even this is plenty in my book. So he does this amazing paper. You can think of him as being the inheritor of Kalman. This guy says, give me inputs, give me outputs, and I am going to create for a linear problem. And then I'm going to give you a minimal balanced realization. So those of you that do control stuff, you know all of this. The basic idea is, how do I find a linear dynamical system which, given these inputs, gives you these outputs and has certain robustness properties? And so think of this as being the two-dimensional parameter space. For my example, my little Takens-Bogdanov example, I don't know beta 1, beta 2. I just know that there is in principle a two-parameter space. And this is a blind monkey. And what the blind monkey does is that he turns some dials, and by turning some dials, you decide where to throw a dart in this parameter space. And this dart chooses what the conditions are that we're going to do measurements. And then what we do is that we do, let's say, 500 measurements. These 500 measurements, think of them as 500 different initial conditions. You don't know which initial conditions, but you know the changes from wherever the initial conditions are. You see, I've chosen them, these initial conditions, to be kind of reasonably distributed over the phase space, but I have no idea what the phase space is. I just get 500 time series. The only thing that I really know is that these 500 time series, they were obtained together. They were obtained at the blue conditions. And then the monkey kind of turns the things again, and he throws additional darts. And so let's say he does 100 different experiments. And for each experiment, you get 500 measurements. And so you have 100 experiments at 500 measurements each. And the only thing that you know is that the 500 blue hairs, think of it as hairs on a shag carpet, the short transients, the 500 blue hairs were obtained at blue conditions, and the 500 yellow hairs at yellow conditions. But you don't really know what the colors are. You just know that there is 100 experiments, and for each experiment you have 500 measurements. And so you kind of shear the carpet and take all of these measurements. So you have now 50,000 hairs. You throw them in a sack and you shake the sack, and the only thing that you know is that blue goes with blue, and red goes with red, and yellow goes with yellow, and you don't even know that they are red and yellow. You just know that there is a bunch of these hairs, 500 of them, that have a label, and the label is 19. So you take 50,000 here, and this is the worst part of my talk, and I hope I can kind of do a semi-decent job. These are 50,000 two-dimensional functions. There are two variables, delta x, delta y, as a function of t for a short time. So each one of these hairs, you can think of it as a short time series of delta x and a short time series of delta y. And now what you do is that you have these 50,000 objects, and what you do is that you do data mining on these 50,000 objects. For example, you do diffusion maps in these 50,000 objects, and you find that you can embed them in some low-dimensional space. And now that you have embedded them in a low-dimensional space, you can compare them. You can use a distance between these. You understand? When you do this, you compare them as hairs. You don't know which hairs were in blue conditions. You don't know which hairs were in yellow conditions. You just look at whether two hairs look the same, independent of what conditions they were obtained at. But this is supposed to give you a sense of the embedding. It's the worst slide that I have. But now that you have some sense of how to compare different hairs, what you do is that you take all the hairs that were obtained at conditions 19 and all the hairs at conditions 24, and you take these two sets, and then you do so you do an earth mover's distance between the two sets. You compute a distance between the sets. And having an idea of the distance between the ensemble 19 and the ensemble 24, the ensemble 19 and the ensemble 30, the ensemble 19 and the ensemble 29, you can start creating a space, a geometry in which you can embed the trials. So now you can have an idea, not only if a hair looks like a hair, but if the ensemble of hairs 19 is close to the ensemble of hairs 24. And maybe whether 29 is halfway between 19 and 24. I like to think of this as giving the hairs a little bit of color, because now when you compare the hairs again, you will not only compare them as hairs, but you can also have an extra entry, and this extra entry is going to tell you whether the conditions at which this hair was obtained were close to the conditions at which the other hair was obtained. That is, not only do you know if they look like as hairs, but you have a sense of whether the parameters that they were obtained were close or not. And this is what you do. You iterate between the hairs and the experiments, the hairs and the experiments, and you keep adjusting your metric, and clearly I'm not doing justice to this, and there is no reason for you to think that this will actually converge, but it does, and there is no theorem yet that it does. Maybe there will be. But the basic idea is, think of it just as a numerical experiment. Eventually you actually figure out the color of the hair. That is, you find out the distance between ensemble 19 and ensemble 24, and then you can put together the experiments that you don't know how they are put together, and then you can put together the parameter space. And so here's the example. It's the Takens-Bogdanov, 100 parameter values and 500 short time series. You see the short time series. And then this is what the result is, and I think it's amazing, and I can say it's amazing because it's Ronen that did it. And when you showed this to me, I didn't believe it the first time, or I kind of was saying, wow, because these are the actual parameter values at which the experiments were done, and this is what the data mining does. It tells you that actually your trials can be embedded in a two-parameter space. This is how they look like. Each one of them is white. When you peel off the little white paper, you find that all the blue ones are together, or the purple ones, the ones that have limit cycles, are together, the ones that have two steady states are together, whatever. You find that the topology is correct. Basically, the parameter space is homeomorphic to the true parameter space, and that's the beginning of it. Because it also tells you that these 500 transients, they can be parameterized also by two variables. And what you see here is what it gives me as a realization, as the realization state variables, psi1 and psi2. And psi1 and psi2 are colored by the physical x and the physical y. You can see the physical x here and the physical y there. So this should give you a feeling that what it gives me is a rotation and slight deformation of what the original x and y are. So it finds out that the parameter space is two-dimensional and gives me the right topology. It finds out that the state space is two-dimensional and gives me the right topology. With some care and with Nash theorem, it is not inconceivable that there's going to be an isometry. And this is the thing for which I do not have a picture to show you. This is something that Ronen is working on now. But this, I think, is the most amazing thing of all. What I told you is that there exists a data mining algorithm which is capable of detecting what are the right parameters, or something that is isomorphic, homeomorphic to the right parameters, something that is homeomorphic to the right variables, and has found a way of getting a relation between one and the other. Now that you have this, you can consider exactly the same machinery, but the input will be the parameters and the variables, and the output is going to be the time derivatives. And if you use the same machinery and you learn that function where the input is parameters and state variables and the output is time derivatives, that function is the generator of the previous surface. That function is the law. That is the rules. That is the nonlinear equation, which is going to show up in some sort of tabulated form and not as beautiful as the normal form would be. So we do get the realization. I know it's a minimal realization. I don't know to what extent it is a balanced realization. This is what we're working on now. And so you're kind of wondering, and I ran over my time, so let me finish kind of with this. What is the mathematics of this? This is Netflix mathematics. This is the mathematics of questionnaires. I told you, I told you that I work with Rafi. This is, in this one, maybe I was a little more of a mathematician, and Rafi was even more of an engineer. He did the data, and we together did the problem where we did the dynamical system equations through data. Here is a pure data thing. There is 5,000 people, so this is a matrix. It's 5,000 by 350 or something. There's 5,000 people. You have no idea who these people are. There is 350 statements. So this is a standard questionnaire, a psychological questionnaire. And what every one of these people does is that he answers yes or no in these questions. You have no idea what the questions are, and you have no idea what the people are. It's the same thing with the Netflix problem. You don't know what the people are, and you don't know what the movies are, but you have patterns of who liked which movie. And if you do exactly, so the people are like the parameters, and the statements are like the measurement, are like the channels of measurement. There's 350 of them, and then instead of having short time series, there's just a 0 or a 1. And if you do exactly what I showed you before for the time series, you get that there was a two-parameter family of parameters. There's a two-parameter family of people. This is how they cluster. So this is also like by clustering, but this is embedding rather than just clustering. And all the people that are light blue are the people that later on, when you peel off the white paper, the psychologists are going to say that they are dysfunctional. And all the people that are red are the people that the psychologists say that are functional. And here is the state space. So these are all the questions, which also seem to live on a two-dimensional manifold. And here is all the light blue questions that seem to cluster reasonably well together. What are the light blue questions? They are the questions that the blue people answer yes, and the red people answer no. And if you can see what the questions are, I'm reading every time that I show this, I show a different, I read whatever. So, I wish I were not so shy. I wish I could get over worrying about things I've said that may have injured other people's feelings. I'm apt to take disappointment so keenly that I can't put them out of my mind. I'm often sorry because I'm so irritable and grouchy. And you understand that this has been done without knowing anything about who the people are and what the questions are. And you also understand that this is a real serious threat for privacy, because somebody can just cluster you with people, and if they know one thing about these people, for example, that they know how to write very good molecular dynamics codes, they will know that you can write very good molecular dynamics codes. But you see, there's much worse things that can happen. And if we can do this, my guess is that Microsoft and Google and whatever have done it for some time, and that scares me a little bit. So now you can kind of see why I said this kind of pretentious title. The thing is, it seems that you can go, the mathematics for being able to go from data to predictions, whether it is more dignified the way that I showed you in terms of balanced realizations, or less dignified but equally effective in terms of deep nets that are doing the same thing, it seems that these mathematics are kind of here or around the corner or whatever, and this is strange. It's a strange feeling. There's good things about this, there's wonderful things to do, but it is also a little bit funny, because what does it mean to understand something? Yes? If you can make predictions and don't know what the laws is this good enough if the predictions are correct? And so what I'm going to do, having run over, is that I'm going to show you two things. The one thing was an advertisement for kind of a nice paper that we did. A part of these calculations is that the data mining, by using something that's called a Mahalanobis distance, that is, by rescaling things by the variance of the noise in the neighborhood of the measurements, actually is independent of the measurement instrument. That is, it does not matter if you take a photograph with a light camera or with an infrared camera. It does not matter if you measure, as long as there is monotonicity between what you measure, by Lipschitzness, between what you want to measure and what you measure, the data mining doesn't see it. So the data mining is gauge invariant, and I had, they are invariant to the measurement instrument. And so I wanted to kind of do a little illustration of this. And so this is gauge invariance in music. This is the 4 harpsichord concerto of Bach. And here is, no, stop. You see, this is the thing. I cannot see, in this beautiful whatever, I cannot see where the, but now I can stop it. And now I can tell you what the 4 violin concerto of Vivaldi sounds like. So different frequencies, the same music. This is done in the data. Why is this important in the data? Because this means that you can fuse information no matter what the measurement instrument is. And then the last thing that I will finish with, I had something more about gauge invariance, but it doesn't matter. This is a slide that I already showed you. It's calculus, but it's calculus in the right variables, because then we can do small steps and search better and get predictions without necessarily knowing what the equations are, by just doing neighbors. And this is Newton, since we're here. And then I'll finish by just telling you something about this Zuse guy who did the computer in 1941. So because I was going to give this talk in Germany, I found this book that has a whole chapter on him, including photographs. And yeah, some of you already laughed. I was a student in civil engineering in Berlin. Berlin is a nice town, and there were many opportunities for a student to spend his time in an agreeable manner. There was a number of politically incorrect things here. But instead of that, we had to perform riesige, schreckliche calculations. And so he built a computer, and what we do is that we build algorithms so that we can go out on the town and have a good time instead of doing riesige, schreckliche calculations. Thank you.
Are there any questions?
The game is starting, I think. Ask one thing. Yes?
I'll ask a question. You were talking about these, the lifting and the umbrella sampling, and could you say a little bit
Yeah.
more about that if it rules out certain approaches?
So the basic idea is you have a slow manifold, you have a sense of where it is, and now you want to have a pretty good idea of where a point on it further away from where you are. So what you do is that you extrapolate, this gets you off manifold, and now how do you get back on? If the manifold is very attracting, just a simple quick simulation will bring you down. Maybe you don't have a lot of control where exactly it will bring you down, but it doesn't matter as long as you sample enough. Maybe if the manifold curves violently, you will go out here and then you're not going to drop. So it is conceivable that if you go here, you can let it free, or you can do a little bit umbrella sampling on some, on like the local principal components, like Plume does, and it'll bring you down. Just a preparatory step. For those of you, remember I told you I'm a bifurcation guy. This is exactly like continuation on branches. You have a branch of solutions up to now, you make a prediction step, and then you need a correction step. What is your correction step? You can get the steady state at that parameter value. Remember? So this is for us bifurcation people. Here's the branch of solutions. I am sitting here. I've computed up to here. Here's my extrapolation. I can try and find the steady state at that parameter value. I can try and find the closest steady state. There is all kinds of things that you can do.
Come back to your original illustration with the
Yes.
hydrodynamics and the G of R.
Yes.
You need the microscopic code to be able to do all this.
Yeah, and so you need
You
lifting.
can't
Yeah.
do this if you just have a G of R.
No, and so this is a very good point, and this is maybe the one piece of empirical wisdom. What we do is that we have three sets of variables. There is the very, very detailed variables. There is the very few parsimonious diffusion map variables. And then here is like 15 principal components. Now, if you have a 1D manifold, then locally you can parameterize it by one local principal component. Yes? But since it is a 1D manifold, the second, third, fourth, fifth principal components are going to be functions over the first principal component. So we extrapolate these functions. Okay? So this is you understand, this is now the ugly underbelly of the story, but this is what we do and it works. And let me also say geometric harmonics, for those of you that play with diffusion maps, is a way of doing this in a more dignified harmonic analysis way. But I told you the principal component business because I think this is something that everybody would understand. Yes?
In the sense that with diffusion maps you can reduce a 1,000-dimensional space to like few dimensions.
If it's reducible.
Yeah, but how do you decide how many low-dimensional variables do you need? For instance, if you consider the first example you gave with rectangle,
Yeah.
have the second eigenfunction is 7th. So in principle you need 6 or 7 variables.
No, good
Y.
point. Okay, so I will take the easy way out. It really was 2, but what happened was that the second, third, fourth, and fifth, sorry, the first is trivial, the second matters. The third, fourth, fifth, and sixth were harmonics of the first.
That's right.
If you remember your trigonometry, cosine 2x can be written as a function of cosine x. Therefore, if you look at the data in cosine x, cosine 2x space, they will not fill up space, there will be a curve. You can write an algorithm that does this, so it will filter out who are the harmonics and then see who the next new one is. How many of the new ones to keep? Oh, gee, it's the same as principal components. You decide what you think is noise in your system. This is a very, I apologize for saying this, but at some point you have some sense of, how much energy do you expect to have in your signal and how much is noise. There is better ways of saying this, but so the harmonics you can factor out. What do you want to consider as noise? Where is the knee in your energy? That's another story. Yes.
I enjoyed your talk very much.
Thank you.
A remark and a question, if I can. The last example where you had 5,000 people and 350 questions,
Yes.
I guess you're just computing the Fiedler eigenvalue of the graph Laplacian and then looking at the clustering of the associated eigenvector.
Yes, what I did is that I wanted to tell you that this problem, so maybe if you want to remember one thing from the talk, is that what I told you that this problem doubles as probably finding some sort of normal forms for dynamical systems. So if you do it on data, then it does what you said, and that's what Rafi does. But if you don't do it on data, but you do it on models, then it actually has implications and history and realizations, and it's important. So by clustering and balanced realizations, in a way, are the same thing. So this is what we learned, right? This is what we learned by doing this. Else, the bi-clustering was something that Rafi had done without needing. Yes.
And my question in terms of the where you recreate your dynamical system of 2 dimensions with 2 parameters, you had 50,000 hairs, I think.
Yes.
If you had a much more complex model, I guess you need many hairs and you need many iterations.
Any answer I give you, you would also. There is a lot of common sense things, and basically, okay, I'm going to say something very cheap. We aren't. Okay. As I tell my friends, and again, I am not an SD person. I told you many times I'm a nonlinear dynamics algorithms guy. The thing that is missing for me is a lot of hypothesis testing. We need hypothesis testing as to whether this is indeed describable by 2 or 3, if this is an SD with white noise or with Levy flights, if this is a PD, if this is a local or not a local equation, if this is a... So all of the things that upon inspection, when you have a written model, you can just see because they are written in front of you, we need good tests for these things. And there is a lot of this that I think is very necessary. In my opinion, this is the most lacking thing. Like this is the thing I wish, I would pay good money for somehow, if you want. And I think you have a feel. There are people that do this. I mean, I'm sure there is many, but I mean, Greg Pavliotis, for example, my friend at Imperial, is one of the people that do this. And I have done some very cheap versions of, all of you, I'm sure at some point have checked that the autocorrelation dies very quickly and that the variance grows linearly, or, there are simple things that everybody would do on data, but there is much more complicated things. One thing that is good that I can tell you is that it's one thing to decide, I don't have enough data to decide, all right? And it's another thing that I hope we do make a contribution towards. If you have a little bit of geometry, then you kind of know and can parameterize which are the directions in which you should go and collect more data. And so one of the things that I do think this thing will help is not only identify what is bad, but maybe also give you a sense of where to go and collect data to do this. And now that I also, as I said this, I see Radek, I should say that the basic idea, I only did an advertisement in this, that the data mining, among other things, is gauge invariant. This is something that was done by Amit Singer in a paper with Koifman when he was a postdoc at Yale, and then we did it with him, with Radek, where we called it anisotropic diffusion maps. But the basic idea, and I still didn't understand that it was gauge invariant. I think I understood it a couple of years ago. That if you use the local noise to scale the local, so you see there is a little miracle that happens. If the distances are small and you use the noise variance to rescale the coordinates, then the distance is insensitive to fourth order, invariant to fourth order, to the measurement function, as long as the measurement function is by Lipschitz. So what this says is, as long as what you measure is 1-to-1 with what you want to measure, this is a way of doing diffusion maps in a reference space where the noise is diagonal. So it doesn't matter what the measurement instrument is, and what this means then is that you can also, among other things, you can, as I told you, you can fuse data from very, very different measurements. So you can have, but this is one of the things we do. You take molecular dynamics data, and then you take Monte Carlo data or kinetic data, and as long as you do the data mining in a careful way, with the noise of the molecular dynamics and the noise of the kinetic Monte Carlo calculations, it is conceivable, and it does work in some cases, that you can actually fuse these informations together. Okay.
I think we should thank Ioannis once again for the inspiring and entertaining talk.
Thank you.